All right, welcome to The Explainer. Today, we're going to tackle one of the most powerful and honestly game-changing ideas in all of software design. I'm telling you, once this one clicks, it'll change how you write code forever. I'm talking about the Liskov Substitution Principle. Ready to see what all the fuss is about? Okay, let's just dive right in. Now, here's the key to this whole thing. It all comes down to this one idea, the contract. That's everything. You got to think of it like a promise. If a class makes a promise about how it's going to behave, then any class that inherits from it must keep that exact same promise. No ifs, ands, or buts.
So to really get a gut feeling for what this contract means, let's forget about code for just a minute. We're going to use a simple analogy, and I love this one because it makes a kind of tricky concept super easy to grasp. Let's talk about a juice machine.
And this right here perfectly captures the spirit of the Liskov principle. The machine's contract is simple. You put fruit in, you get juice out. So an orange works perfectly, right? You get juice. Now, what if we substitute an apple for the orange? It has to fulfill that same promise. If putting that apple in jams the gears or just gives you an error, then that apple isn't a valid substitute, even though it's technically a fruit. It broke the contract.
Okay, so now that we have that juice machine idea in our heads, let's bring it back to the world of code. We're going to look at a classic problem that seems super simple on the surface, but it's surprisingly tricky. This is where the rubber really meets the road. And this right here, this is the trap. This is the one that gets everybody. In geometry class, of course, a square is a rectangle. So it seems like a perfect situation for inheritance. But the Liskov principle warns us that what matters isn't the label we use in the real world. What matters is the behavior in our code. And here is the conflict, clear as day. The rectangle class makes an unspoken promise, its contract. It says, you can change my width and height independently. But a square subclass, well, to stay a square, it has to break that promise. If you change its width, you are forced to also change its height. That's a fundamental mismatch in behavior. So picture this. You've written a little function somewhere in your application, and it's built to work with any rectangle object. Its job is simple. Set the width to 5, set the height to 10, and calculate the area. It completely trusts that rectangle contract. I mean, we see code like this all the time. But here comes the bug. We pass a square object into that function. The code sets the width to 5, which also sets the height to 5. Okay, but then the next line sets the height to 10, which forces the width to also become 10. So the area we expected was 50, but the result we actually get is 100. Our program is just plain wrong now, all because we made a substitution that broke the contract. That silent, unexpected failure is the exact kind of nightmare that the Liskov principle is designed to prevent. So now, let's get into the nitty-gritty and look at the formal rules that will help you avoid this kind of mess in your own code. This is how we build predictable, reliable systems. And there it is, the big idea. It sounds simple, but it's so powerful. It just means that anywhere you use a base class, you should be able to swap in any of its subclasses, and the program shouldn't even notice. No surprises, no weird side effects, no quiet little bugs. The substitution has to be totally seamless. And this is basically how we keep that promise. Let's break it down. First, the subclass can't be pickier about its inputs. Second, and this is the one our square violated, it must deliver on all the promises and outcomes of the parent. And third, it can't just start throwing new, unexpected types of errors. It has to honor the contract from top to bottom. Okay, we've gone through the rules, we've seen the classic square and rectangle puzzle, but now let's talk about why this is so critical. What does this mean for the actual code you're shipping to production, day in and day out? Let's make this real. Imagine you're building the checkout system for a huge e-commerce site. You've got a base payment class, and it has a method called process refund. Now, a new requirement comes in. A special one-time offer payment type that is non-refundable. If you just create a subclass for it, you've basically just planted a time bomb in your code. Because now, any part of your system that's built to handle any payment might suddenly get this new, non-refundable one. When it calls process refund, what happens? Does it crash? Does it fail silently? Either way, the behavior is broken, and now you're staring at a cascade of errors that could bring your whole system to a grinding halt. So here's what I want you to take away. This is the ultimate test. The next time you're about to write class B extends A, just stop and ask yourself this one simple question. If the answer is anything but a confident absolute yes, you are looking at a Liskov violation. You need to step back from the keyboard and rethink your design. Your future self will thank you for it.